In this video, we are going to talk about how to find the derivative of an inverse function. So as a reminder, if f is a 1, 2, 1 function, differentiable function, then its inverse function, f inverse, is also differentiable. Then we're not going to go into the detailed proof of why this is the case. However, kind of the idea for this is the graph of f inverse is a reflection of the graph of f across the line y equals x. And so to get the inverse, you just flip all of the x and y coordinates, so the graph is just this reflection. So if the graph of f was smooth and had this differentiable property, the graph of f inverse also will, with the one caveat being this only applies to places where f, f inverse does not have a vertical tangent line. And so we could introduce vertical tangent lines when we do this reflection process. And so possibly there could be some places where f inverse isn't going to be differentiable. Those would correspond to places where you had horizontal asymptotes in f. And so what we're going to do is we're going to use implicit differentiation to find the derivative of these inverse functions. So we're going to first start by looking at log functions. And so we want to compute the derivative with respect to x of log base b of x for b greater than 0 and b not equal to 1. If b is equal to 1, this is kind of a weird function, and so we're not going to allow b to be 1, and b being greater than 0 is just to avoid negatives like we always do. And so the trick we're going to use is if we let y equals log base b of x, we want dy over dx. Okay, so if I just let y be the log base b of x, what we're looking for then is dy over dx. But y equals log base b of x if and only if x equals b to the y. And so this is the idea of inverse functions. If you just raise both to b exponentiated to both sides, we'd have y to the b on the left-hand side and just x on the right-hand side. And this is because b to the log base b of x is just equal to x. So we're just taking b exponentiated to both sides. So y equals log base b of x if and only if x equals b to the y. But we know how to do the derivative of b to the y. And so what we're going to do is we're going to take the implicit derivative of x equals b to the y. So the derivative with respect to x of x is just 1. And the derivative of x with respect to x of b to the y, well, this is going to be with the chain rule, b to the y ln of b times the derivative of y, which is just dy over dx. And so we took the derivative using the chain rule here, where our outer function was b to the x, and the inner function is y. And so we set these equal to each other then. So we've got 1 equals b to the y ln of b dy over dx. And so dividing, we get 1 over b to the y, ln of b, equals dy over dx. And so we have found then our derivative for y. But notice it has a y in it. We'd prefer to only be in terms of x since we started with something only in terms of x. Our original equation was y equals log base b of x. So we want to get rid of this y term. But we know that x equals b to the y. And so just plugging that in, we get dy over dx equals 1 over x ln of b. And so that then is the derivative. So we have found that the derivative with respect to x of log base b of x is just going to be 1 over x ln of b. That's what we've just computed using this process. Now, a special note is that the derivative with respect to x of ln of x is 1 over x ln of e, but ln of e is 1, so this is just 1 over x. So kind of how e to the x had the simplest derivative, its corresponding inverse ln of x has the simplest derivative. So we're going to use the fact we now have these derivatives to compute some examples. So we want to find the derivative of y equals ln of x squared minus 6. And so this is just going to be a regular explicit derivative. We're going to do some examples of that just to kind of practice. And so we have dy over dx. Well, we've got a composition of functions. Our outer function is the ln function, and so I'll write that down. Our outer function is ln of x. Our inner function here is x squared minus 6. The derivative of ln of x is 1 over x. The derivative of x squared minus 6 is 2x. And so plugging things in, we get 1 over the inner function, so 1 over x squared minus 6, times the derivative of the inner function, which is 2x. And so for our derivative here, we get 2x over x squared minus 6. And so that's just using the chain rule. It's fairly straightforward given the fact that we now know the derivative of ln of x. Another example, we want to find the derivative of f of x equals ln of cosine of x. Okay, so this is going to be very similar to the previous example. So f prime of x, the derivative of ln is just 1 over x, so we're going to have 1 over our inner function, which is cosine of x, times the derivative of our inner function. So we get 1 over cosine of x times the derivative of cosine is negative sine. So this gives us negative sine of x divided by cosine of x. But that then is equal to negative tangent of x. And so the derivative of ln of cosine of x is just a negative tangent of x. And so next, we want to differentiate f of x equals log base 10 of 2 plus sine of x. Now we're just going to do this one to make it clear how we do things that don't involve natural log. So our base here is 10. And so that means the derivative with respect to x of log base 10 of x is 1 over x ln of 10. So that's just going to be our derivative of log base 10 of x. And that's our outer function. And so using the fact it's a chain rule, the outer function is log base 10 of x, which is a derivative of 1 over x ln of 10, as we just saw. And then our inner function in this case is 2 plus sine of x, and its derivative is cosine of x. So then the derivative f prime of x is going to be the derivative of the outer function, evaluate the inner function, so 1 over x ln of x. But x gets replaced by our inner function, which is 2 plus sine of x times ln of 10. And then multiply that by the derivative of the inner function, which is cosine of x. And so we get an answer here of cosine of x divided by 2 plus sine of x ln of 10. Okay. So one final example that we want to look at when it comes to logarithms is we want to find the derivative of f of x equals ln of the absolute value of x. So this is a piecewise function. Remember, absolute value is piecewise in nature. And so what this then tells us is our f of x function is going to be equal to just ln of x if x is greater than 0. And it's going to be ln of negative x if x is less than 0. And at 0, ln is not defined, so we don't have to worry about that. Okay? And so we've just defined our function. We've split it up using the property for how absolute value behaves. And so now we can take the derivative like we normally would. Remember, for a piecewise function, what we do is we take the derivative in pieces. So we just take the derivative of the separate pieces, and then we have to restrict the domain if it overlaps, possibly. So the derivative of ln of x we know is 1 over x, so this occurs if x is greater than 0. And then the derivative of ln of negative x, well, the derivative of ln of x is 1 over x, so we get 1 over our inner function, which is negative x, times the derivative of negative x, if x is less than 0. And we don't have to worry about what happens at 0, where we would change equations, because ln is not defined there. And so we then have that the derivative is equal to 1 over x if x is greater than 0, and then it's going to be 1 over x if x is less than 0 as well, because the derivative of negative x is negative 1. So negative 1 over negative x is just 1 over x. Now what this then tells us is that the derivative of ln of the absolute value of x equals 1 over x if x is not equal to 0. And so this function, it looks a lot like the natural log function in its derivative. It's got the same derivative, but it has a larger domain. And so this is just kind of a handy thing to be aware of, is that we do have another function with a derivative of 1 over x, but its domain is bigger. So that is all we want to look at for logarithm functions. But logarithms are not the only type of inverse function. And so we want to find the inverses of the inverse trig functions now. So recall by restricting the domain, trig functions have inverses. Okay, so if you restrict the domain appropriately, the trig functions have inverses. So we want to know how to compute the inverses of the trig functions. So we're going to do basically the same thing we did for logarithms, and then we're going to have to do something slightly different, but the derivative part is the same. It's just how we get rid of y that will be different. And we'll see that as we go through. And so we want to find the derivative of y equals sine inverse of x, which, just as a reminder, we sometimes write this as arcsine of x. So those are the same function, sine inverse and arcsine. So what we're going to do is we're going to take sine of both sides. And so we'd have sine of y equals sine of sine inverse of x, but sine of sine inverse cancel, so we're just left with x. So sine of y equals x. So now that we have sine of y equals x, we're going to take the implicit derivative of both sides. So we've got the derivative of sine of y. Well, that's going to be cosine of y times dy over dx, just using the chain rule. And then the derivative of x is 1. So what we found then is that cosine of y, dy over dx, equals 1. So dy over dx equals 1 over cosine of y. So up to this point, what we've done has been the exact same as what we did for logarithms, in that we just found what x was in terms of y by using the inverse property, and then took the derivative implicitly. But now we need to get rid of our cosine of y. And so the process for this is the same for all trig functions. I'm just going to do it in this example, but you would do the same idea for any of them. So what we know right now is that sine of y equals x. And so we're going to draw a triangle, with one of the angles being y. And so we've got this triangle, the right triangle, with an angle of y. And now we know that sine equals opposite over hypotenuse, but that's x. So the opposite is x, and the hypotenuse is 1. Then by the Pythagorean theorem, the adjacent side is square root of 1 minus x squared. And so that gives us a right triangle. But now we can use cosine's formula, which is adjacent over hypotenuse, to get cosine of y. And so using this triangle, cosine of y must be the adjacent side, which is square root of 1 minus x squared, divided by the hypotenuse, which is 1. So we just get square root of 1 minus x squared for cosine of y. And we can plug that in then to get dy over dx equals 1 over the square root of 1 minus x squared. Or in other words, the derivative of sine inverse of x is 1 over the square root of 1 minus x squared. And so we've computed then the derivative of sine inverse. Now I'm going to list the derivatives for all the inverse trig functions now. You compute the other 5 doing the exact same trick we just barely did, using the fact you know the derivatives of the 6 trig functions. And then you draw a right triangle and figure out how to replace y in your equation that you get from the implicit derivative. And so the following are the derivatives of inverse trig functions. So we've already got the one we computed before, the derivative of sine inverse of x. It's 1 over the square root of 1 minus x squared. The derivative of cosine inverse of x is negative 1 over the square root of 1 minus x squared. The derivative of tangent inverse of x is 1 over 1 plus x squared. The derivative of cosecant inverse of x is going to be negative 1 over x, square root of x squared minus 1. The derivative of secant inverse of x is 1 over x, square root of x squared minus 1. And the derivative of cotangent inverse of x is negative 1 over 1 plus x squared. And so those are the derivatives of our 6 inverse trig functions. Now notice that they kind of come in pairs, just as we saw for the derivatives of trig functions. So sine inverse and cosine inverse just differ by a negative, and secant inverse and cosecant inverse differ by a negative, with tangent inverse and cotangent inverse differing by a negative. And the co is the one with the negative. So that's a way to remember this, is that they come in pairs with sine and cosine, secant and cosecant, and then tangent and cotangent. But the co is the one with the negative, while the non-co is the positive. And so we're going to use this now to compute some derivatives. So we want to differentiate y equals 1 over tangent inverse of x. Okay, so this is 1 over tangent inverse of x. And so we can do this two ways. We can either use the quotient rule or we can use the chain rule. We use the chain rule a lot, so I'm going to use the quotient rule here. So we've got dy over dx is the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared. The derivative of 1 is 0, so this first term just becomes a 0, so we have 0 minus 1 times the derivative of tangent inverse, well, that's 1 over 1 plus x squared, then dividing this by tangent inverse of x all squared. This one, multiply the top and the bottom by 1 plus x squared, just to get rid of the mixed fraction that we have. So this gives us negative 1 divided by 1 plus x squared times tangent inverse of x quantity squared. So that is our derivative then of 1 over tangent inverse of x. So next, let's find f prime of x when f of x is equal to x arc sine of the square root of x. So we want to compute the derivative of x arc sine of the square root of x here. And so we're going to use the trick that we've done before, namely this is a product of two things, so we're going to use the product rule. So the derivative of this function will be the derivative of the first thing, which is x, times the second thing, which is arc sine of the square root of x, plus the first thing times the derivative of the second thing. The derivative of x is 1, so we're going to get 1 times arc sine of the square root of x, plus x times the derivative of arc sine of the square root of x. Well, the derivative of arc sine is 1 over the square root of 1 minus x squared, but our x is square root of x by the chain rule, so we get 1 over the square root of 1 minus the square root of x squared, and then times this by the derivative of our inner function, which is the square root function. So simplifying this, we have arc sine of the square root of x plus x times 1 over the square root of x squared is just x. This is the square root of 1 minus x times the derivative of the square root of x is 1 over 2 square roots of x. So this becomes arc sine of the square root of x plus x times 1 over 2 square root of x square root of 1 minus x, which this then becomes arc sine of the square root of x plus, we can cancel off part of this with the square root of x here to get a square root of x in the top, divided by 2 square root of 1 minus x. And so that then is our derivative for x, arc sine of the square root of x. So one more example to look at. So now we want to compute the derivative of y equals ln of secant inverse of x. And so this is a composition of functions. Our outer function is ln of x, and our inner function is secant inverse of x. The derivative of ln of x is 1 over x. The derivative of secant inverse is 1 over x square root of x squared minus 1. So then we have that dy over dx equals the derivative of the outer function, which is 1 over x, but we have 1 over the inside function because we're using the chain rule. So 1 over secant inverse of x times the derivative of secant inverse of x, which is 1 over x squared of x squared minus 1. So we end up with 1 over secant inverse of x times the square root of x squared minus 1 times x, which I'll put in front. So that's then the derivative of natural log of secant inverse of x. Just kind of combining the two that we've done before in this video with ln of x and secant inverse. So that is then how we compute the derivative of inverse functions, namely for logarithms and inverse trig functions.